The chapter is real numbers for standard 10 and this is part 14. So some more problems related to the applications of Euclid's division lemma. We have been doing these type of problems in our previous videos. So here show that the square of an odd positive integer can be of the form 6q plus 1 or 6q plus 3 for some integer q. So we know that any positive integer can be written in the form of, so now since it is 6 here, so we will have to take it as b as 6, so 6m plus 1, 2 with remainder as 0 to 5. Now if here we have to take the square of an odd positive integer. So from this if you see 6m is a even integer. So 6m plus 1 will be an odd. So 6m plus 3 and 6m plus 5, these are the three odd positive integers. Now we have to find the square of these integers and then prove that that is of the form either 6q plus 1 or 6q plus 3. So odd positive integers are these. Now when x is equal to 6m plus 1, x squared is equal to, because you have to find square. So x square is equal to 6m plus 1 the whole squared. So a plus b the whole squared identity you are using. So you write it like this. Now we have to write it in the form of 6q plus 1 or 6q plus 3. So from this we will take 6 as a common factor and then you can write plus 1. So this is of the format 6q plus 1 where q is equal to, you have to write this. Now similarly for x is equal to 6m plus 3, the same thing, you square it, x squared. Now here it is 9. So if you take 9 as a common factor, you cannot bring it to this format. You have to take only 6 as a common factor, then only you can write it as 6q. So we will write 6 into, now here 9 you can write it as 6 plus 3. So that 6 will be, the 6 will come in along with this and 3 will be separate. So 6m squared plus 6m plus 1 plus 3. So 6q plus 3. So this takes this format. And then when x is equal to 6m plus y, x squared is equal to, here again 25, we have to of course take 6 as a common. So 6 into 4, 24. So the remaining will be 1. So plus 1. So this will take the format of 6q plus 1 where q is equal to this. Prove that if x and y are odd positive integers, then x squared plus y squared is even but not divisible by 4. So x and y are odd positive integers. So we can always write an odd positive integer as 2q plus 1 for some integer q. For even you write 2q, for odd we write 2q plus 1 is a general format. So now x and y are odd positive integers. So the format will be x is equal to 2m plus 1 and y is equal to 2n plus 1. You cannot have the same number because both are two different odd positive integers for some integer m and n. Now we have to do x squared plus y squared. So x squared plus y squared is equal to 2m plus 1 the whole squared plus 2n plus 1 the whole squared. Expanding, you will get this. You take 4 as a common factor. So this will come inside. Now 1 plus 1, 2. So you get 4q plus 2. You can write this as 2 into 2q plus 1. So now you can write this is an even number because any number multiplied by 2 is always an even. Now we have to prove it is not divisible by 4. So x squared plus y squared is equal to 4q plus 2. Now if Euclid's division lemma, you know a is equal to bq plus r, that is a is divided by a number b, then you get quotient and this is the remainder. So here you are writing 4q plus r, that means x squared plus y squared is divided by 4, you get a remainder of 2. So x squared plus y squared leaves a remainder of 2 when divided by 4, that means it is not divisible by 4. That's what we have to prove. So we have proved, since it is giving a remainder of 2, it is not divisible by 4. Hope you understood this. So, I will meet you again with some more different type of problems on the applications of Euclid division lemma. So, bye for now. Keep practicing.